let sigma be some finite alphabet. In this video, we'll see how deterministic finite automata can be generalized to give us non-deterministic finite automata, which will be a very useful tool moving forward, as well as giving us our first taste of non-determinism. Recall that a deterministic finite automaton over sigma consists of a finite number of states, including a unique start state, and one transition from each state for each symbol of sigma, with some subset of the states marked as accept states. And how this operates for a given input string x is as follows. We start at the start state, follow the transition given by each symbol of x in sequence, accept if we finish on an accept state, and reject otherwise. The term deterministic refers to the fact that as we scan through the characters of an input string, our transitions from each state determine a unique next state. We finish on exactly one state, which gives the result of the computation, accept or reject. This is all due to that second condition, that a DFA must have exactly one transition from each state for each symbol of sigma. In a non-deterministic finite automaton, or NFA, we lift this condition. From each state, we can have any non-negative number of transitions for each symbol in the alphabet sigma, allowing an automaton such as the one pictured. This has two effects. First, the NFA could have multiple transitions from a given state for a single symbol of the alphabet. For example, from the leftmost state, we could have two places to go on a B. Second, it allows the NFA to have no transitions at all for a given state and symbol, as happens on a B from the rightmost state. Due to these changes in the structure of the automaton, we have to adjust our rules for its operation on a given string x, which we'll illustrate on our example DFA with the string x equals AAA, BA, BA, BA. As always, we start at the start state. Also as before, we scan through the input string one symbol at a time from left to right. Given our current state and the symbol we read from the string, we now need to follow all of the corresponding transitions. If there's a unique transition for our current state and symbol, it's business as usual, as happens for the first three A's in our string. If there are multiple transitions from our current state matching that symbol, we need to consider all possible results. We can do this by branching our computation. We can think of this as cloning snapshots of our DFA's configuration, its current state and the string remaining to be read, and having each branch follow a different transition. In our example, we have two transitions for the B, so we split into two branches, one following one transition and one following the other. The next A moves each of these branches clockwise around the states. If there is no transition matching the current state and symbol, that branch of the computation dies. In our example, the right-hand branch dies now on a B, while the left-hand branch lands back on the same state. Note that once a branch dies, it can never finish on an accept state because it will not finish at all. Our next A moves us clockwise. Our next B again splits into two branches, and the final A moves us clockwise by one state again. Our rule for acceptance is that an NFA accepts the string x when at least one branch finishes at an accept state. In our example, one of our branches does finish on an accept state, so this NFA accepts the string AAA, BA, BA, BA. An NFA rejects x when no branch finishes at an accept state. This whole branching thing is a lot to get your head around, but non-determinism and this notion of branching will be a very important concept, and it will come up for every machine type that we see. Just remember that no matter how many branches are generated, for our machine to accept a string, we just need there to exist one branch that accepts it, and it's enough to find just one. On the flip side, an NFA rejects a string just when no branch accepts the string. It's important in this case that every branch is checked. In an NFA, we also allow a special type of transition, called an Epsilon transition, as we see in the NFA to the right. To see how they work, let's suppose that we start processing some string so that our initial state is the start state. When a branch arrives at the tail of an epsilon transition, we immediately add a branch following that epsilon transition if one doesn't already exist, with no symbol read from the input. We continue this procedure with all epsilon transitions until no new branches are added, which is what we'll mean by processing epsilon transitions. In our example, the new branch also is at the tail of an epsilon transition, so yet another branching occurs, leaving us with 3 branches before a single symbol is read from the input string. Note that among the 3 states our branches sit on is an accept state. So this NFA accepts the empty string, despite the fact that the start state is not an accept state. To complete our description of how an NFA operates, we'll add a note to the first 2 steps to process all epsilon transitions anytime the state changes. We'll later see that epsilon transitions are a very useful tool when we want to modify a DFA in certain ways. As with DFAs, each NFA-M either accepts or rejects each string in sigma star, and we define the language accepted by M, written L of M as usual, to be the set of strings it accepts. What about this NFA we've just seen? After our initial branching, an A will get us to the state at the left, and the other 2 branches, having no A transitions, will die. We'll stay at that accept state as long as we see A's, and the branch will die if we see anything else. Similarly, a B at the outset will get us to the state at the right, and the other 2 branches will die. We'll stay at that accept state as long as we see B's, and the branch will die on any other symbol. We can summarize our findings quite simply. This NFA accepts a string X just when it's the empty string, or a string of A's, or a string of B's. Any string containing both an A and a B will be rejected. This union of regular sets is something we've seen achieved by the product construction, but epsilon transitions and NFAs make it even easier. Now, every DFA counts as an NFA as well, so it should be clear that any language accepted by a DFA, that is any regular set, is also accepted by some NFA. But NFAs seem to allow us to do more complicated computations. So the natural question is, can an NFA accept some non-regular set, which by definition no DFA could? We'll see that the answer is, perhaps surprisingly, no. We'll prove this by showing that for any given non-deterministic finite automaton, we can construct a deterministic finite automaton accepting the very same set. This is the end of our brief introduction to non-deterministic finite automata. These loosen the restrictions on transitions, allowing any non-negative number of transitions from each state on each symbol of sigma, as well as allowing epsilon transitions. They give us our first taste of non-determinism via branching, and non-determinism is a big deal. We'll further discuss non-determinism and the relationship between NFAs and DFAs in the next video. Then we'll use NFAs to show that products and asterisks of regular sets are regular.